In this video, we're going to be continuing our study of fundamental relations, Maxwell relations, and the use of measurable quantities. And as a reminder, measurable quantities are pressure, volume, temperature, C sub P and C sub V, and then sometimes also this beta and kappa, which are derivatives of volume with temperature or pressure. So we want to look at how U changes with temperature and volume next. So what we were doing in the previous video, we say, I can use calculus. du is how U changes with temperature times dt, plus how U changes with volume times dv. And du dt at constant volume is C sub v. What's the big deal? So all I have to do is come up with this. Okay, du with volume. The differential for du, the fundamental relation, is TdS minus PdV. So I'm going to take this and turn these into derivatives with volume. So ds dv at constant temperature and dv dv at constant temperature. Now dv dv is equal to 1. No problem. So I get minus p. I still have this one though, this TdS dv at constant temperature. Now S is the most unfortunate one. Okay, whenever I see S, I'm going to next go to the fundamental, or to the Maxwell relations, excuse me. And so I have a Maxwell for that. ds dv at constant temperature is dp dt at constant volume. And so we could simply use this and we end up with this expression right here. The only thing that's wrong with this expression is frequently my definition of an equation of state is not pressure equals blah, blah, blah. So I could take the derivative with temperature holding volume constant. If you have an equation that says P equals, then just take the derivative and you're good. If you truly are being told that you must force it into those measurable quantities, they are all derivatives of volume with temperature or pressure. And so we need a math tool. So the math tool we're going to use is the triple product rule. This is typically derived in a Calculus 3 course or an advanced math course. It is just a consequence of the relationship between partial derivatives of a single function. But if I have three variables that are interrelated, x, y, and z, how x changes with y holding z constant is negative dx dz holding y constant, dz dy holding x constant. Now visually it says dx, and I've got that right there, over dy right there, and then I've got dz's changing, and it looks like they ought to cancel. And so where did this negative come from? It comes from the fact that the paths keep changing. Okay, so this is something that when you need it, you really probably need to look this one up. Okay, now in our case, I have dp dt at constant volume, so I'm going to let x equal p, t equal y, and v equals the z. So if I apply all those transformations there, I end up with this chunk becomes this, dp dv at constant temperature times dv dt at constant pressure. I have the definitions of kappa and beta are for volume. So this is just 1 over that. So I end up with this. There is a negative sign that was in there originally. That negative sign still needs to be there. I can't see it. It shows up again over here. I end up with this. Okay? So we end up with du is cv dt plus beta t over kappa minus p dv. Again, this is a fine answer right here if you are able to take this derivative. So let's again, kind of our test on all of these is, let's try it out with an ideal guess. See what happens there. See if it agrees with what I already understand. So in this case, I have beta t over kappa. Beta is t divided by t. Kappa is 1 over p. Play with the algebra a little bit. I end up with p minus p, 0. And so I have cv dt plus p minus p dv, or just cv dt, the expected result. So let's look at how H changes with temperature and volume. We're going to go through the same steps again and again. So I first start with the calculus definition. dH dt at constant volume plus dH dV at constant temperature times the appropriate differentials. Then for each of these, use dH equals T ds plus V dP. So T ds dt at V plus V dP dt at V. This one, T ds dV at T plus V dP dV at T. Okay, so these steps are pretty much universally the same, every single problem. Now then start looking and seeing where I can use definitions. This turns out to be CV. This is that V dP dt at constant volume. It's that same little trick we just had a moment ago, right? This is going to be a Maxwell relation that gets me out of that. Whenever I see S in a differential, if it's not C sub V, then check out the Maxwells. And then I have this. So now these are all things that if I have an equation of state model, this is all well known. This is a great form right here. If I need to turn it into measurable quantities, I would be able to go through and use the triple product rule. What about what happens for an ideal gas? Okay, well, we're getting pretty good at that. Ideal gases I can solve. P equals RT over V. So the derivative of P with respect to T is R over V. Multiplied by V, I end up with CV plus R. Here, again, this is going to be RT over V. RT over V squared, negative. The V's cancel. This ends up being 0. CV plus R is the same thing as C sub P, and I will correct that in the slide. C sub P right here. Okay. But how does S change with T and V? Well, start with the calculus rule. ds is ds dt plus ds dV dV. This one is going to be a definition of C sub V. This one, it's not a ds dt, so therefore it's going to be a Maxwell relation that gets me out of that. And I end up with this expression. Okay. Now, I can use work we did earlier and know that that's beta over kappa and get it this way. I can also apply an equation of state and take the differential. And so for an ideal gas, end up with this. These should be getting sort of routine, not saying that's easy, but the steps are fairly similar. The first two steps should be just, I don't know, tedious, but the same every time. Then we get to playing the matching game and it starts getting a little bit trickier. And one of the things that's always recommended is compare it to an ideal gas. Even if you're going to eventually use this for a real gas, if you compare it for an ideal gas, you have confidence that your definition is correct. So we're going to pause the video. We're going to move on to another video lesson. We're going to be looking at Gibbs energy as a generating function. It's going to be very special for us. And then also looking at a practical example.